So now we finished talking about the unitary representation of a group. Now we want to move on to the L1 of this group, okay, the L1 space. So as it turns out, the representation of a group is closely related to the representation of the L1 space, okay? So if you recall the L1 space, we actually put a Banach star algebra structure, meaning it has a multiplication, it has an involution. And as you know, the bounded linear operator on a Hilbert space also it has a Banach star algebra structure. You can multiply to operator, and you can do the involution, basically the operator adjoint. All right. So because they both have these kind of star algebra structure, you can move one to the other by talking about these kind of star representations. So here's the definition. So we say a continuous star representation of the L1 space, of the L1 of G, is essentially just a star homomorphism from the L1 of G to some B of H. Okay, so again, H may depend on pi, so let's say it's H pi. And the continuity basically follows from this pi. If you take any L1 function, pi of f, this operator norm, has to be bounded above by the 1 norm. Okay, so you can think about it as a contractive map from the L1 of G as a Banach algebra to another Banach algebra. All right. So here the star homomorphism is really just saying, so this part is really just saying pi of, if you want to convolute two things, then this is the same as pi f times pi g, the product of them as a operator. And if you do the f check, the involution, then this is essentially just the adjoint of your operator. All right. And just a slight note, we also say this pi is called non-degenerate. So pi is called non-degenerate. If the following thing happens, so if for every h inside your h pi, and if this h is kind of annihilated by your entire pi of L1, so pi of L1 of G, if you apply to h that's equal to 0, that would just imply your h is equal to 0, okay? The reason we only care about the non-degenerate is roughly the idea that if you have a pi as a star representation continuous, then you can always plug into a bunch of zeros, okay? So you plug in a bunch of zeros because right now you're talking about representation of a algebra. Initially you don't really have anything about the unitary or anything like that, okay? So when we talk about representation of a group, you don't need this non-degeneracy because, well, you can't really have a corner of all zero. But because your L1 space, you can't really just say it's a representation by some unitaries, for example. This is possible, okay? So you can plug in a bunch of zero space and it's still a valid star representation. It's just these zero are kind of annoying and we don't like them. So let's call them non-degenerate if we can't really find out these zeros, okay? So we only care about the non-zero part, okay? So this is called the non-degenerate ones. And the main goal of this entire lecture is the following idea. So the idea is that now we have a unitary representation of a group, so unitary representation of my group. And on the other hand, I have the star or continuous star representation of the L1 of G. So as it turns out, if I given a unitary representation of the group, I can move to a L1 representation of the L1 space. Okay, so this is sometimes also called the integration of this representation. Okay, I can integrate a unitary representation to a representation of the L1 space. But moreover, I can also do the other way. Okay, so if I start from a representation of the L1 space, I can kind of divide it up and I can make it into a unitary representation of your group. So sometimes this is also called a disintegration theorem. Okay, I know this terminology is kind of I borrowed it from my recent project on file bundles, so there may not be a standard terminology in any books, but I like to see the whole picture as an integration and disintegration. Okay. So in this video, I'm going to talk about the first one, the integration of these unitary representations. So let's start by taking a unitary representation of G on some B of H pi. So this is a unitary representation. So then for every f inside your L1 of G, and you can take any u and v inside this h pi, you can think about this function that's called the I of uv evaluate at f. Let's do the integral of f of x, and then you do the pi x evaluate inner product with the u and v, and then you do the dx, okay? So if you look at this, first of all, this inner product, this pi x u inner product with v is absolute value. So by the Cauchy-Schwarz inequality, you know this is bounded above by the product of these two, the length of these two vectors. But because your pi is a unitary representation, it preserves the length of u, so this is just u times v. All right, so now if you consider the IUVF we just defined, you take the absolute value. So this is less than or equals to the integral of the absolute value of f times the absolute value of the inner product, which is bounded above by the product of these two vectors. And then you do the dx. But this is just the integrate to the one norm of f times the u and then times the v, okay? So this is kind of always bounded by this formula. So because all of these inner product is kind of bounded by some constant and multiplied by these two, the length of these two vectors, so you can always find an operator inside B of H. Okay, so this is basic operator theory. There exists an I pi of f inside B of H pi in the same bounded linear operators, so that this will implement this U and V. Okay, so this I pi of f, if you evaluate at U and V, you take the inner product, this give you the IUV of f. Okay, so that's just how it works. Okay, so this one, what it really does is that this one really looks like the integral of the of your pi of x by this f of x. Okay, so sometimes we write this I pi of f. Okay, what it really looks like is that you integrate the f of x and you do the pi x dx. Okay, you one way of thinking is looks like an operator valued integral. Okay. Operator valued integral. So here the only thing is this pi x is an operator inside B of h pi, but then everything else is integrable, and you can just define it this way, okay? So this one, I pi of f, that's going to be inside the B of h pi, and we know it's going to be bounded by the one norm of the f by the calculation we just did. And this I pi is essentially just defines a non-degenerate star representation, continuous star representations. Okay, so the first proposition we're going to prove is that this I pi, if you think about it from the L1 of G to B of H pi, okay, so that's a continuous star representation, and also it's going to be non-degenerate, degenerate, okay. And moreover, there are also some formula I just want to write for now. So this is the first part, and the second part, I have moreover. If I consider pi of x and I do the I pi of f, so what it does is essentially it's translate this f by x on the left. Okay, so essentially this is I pi of the Lx of f. And if I do it on the other way, so if I do I pi of f, if I multiply by these pi x on the right, so what it does is that, well, it looks like a right translation, but by something inverse, okay? So this is going to be equals to pi of the x inverse times the I pi of the Rx inverse of f, all right? So this is what we're going to prove. Actually, I shouldn't say pi, it should be a delta here, okay? Doesn't make sense to have a pi. It's the modular function, all right? Okay, so here's the proof. So we actually, this I pi of f is, say I pi of f is clearly linear. And we also show that the I pi of f by the norm estimation, we show that this operator norm is bounded above by the one norm, Okay, the reason is just because when you take the inner product, it's bounded up above by these one norm times the length of these two vectors. So let's check the homomorphism part and the involution part. So if I want to evaluate I pi of f with g, so what it does is let's just write it as an operator value integral. Well, technically, you should write it as take the inner product with u and v and you double check, but it doesn't really matter. So let's just pretend we are integrating a bunch of operators. So I have f convolute with g of x, and I multiply by this operator pi x and dx. So the first one is you divide it up. This is just f of y, g of y inverse x, and you have a pi x dx. So here our g is no longer abelian, so I need to be extra careful about where I put the inverse. All right, so now you can do the standard trick. Okay, so you move the y to the outside and you do the g of the y inverse x pi x integrate against dx first. Then I have a fy dy. But inside what you have is you use the left translation. You say, well, let's translate y on the left by y. So I end up with this y inverse get cancelled. So I get integral of the gx, and I have a pi of yx here, and then dx, and then the whole thing fy dy. And now you see that this f of y, that's a scalar, so that can be moved to the left. So let's say that's just the integral of fy gx, and then the pi is a unitary representation, so you have a pi y times pi x. Okay, so you have dx dy. Here the pi x, pi y, they don't commute, but you can move them between this f and g, because f and g, they're just scalar. So you write it as the integral of the fy pi of y, and then you do the integral of the gx pi of x, and then you have a dx, and you can put a dy here. And these two are essentially just the I pi of f times the I pi of g, okay? As you can see, the order really matters here. The pi y have to come before this pi x, okay? So you really have this I pi of f first instead of I pi of g first, okay? So the order now does matter. But in any case, you have this I pi satisfy this homomorphism structure. And now let's consider the involution part. So if I do I pi of the f check, which by definition is just the integrate the f check, this operator value integral. And let me write down the f check. We're no longer abelian, so I do need this modular function, delta x inverse. I have a x inverse conjugate, and then I have a pi x dx. All right. And because now the modular function allows me to rewrite this whole thing as an integrate, basically remove the x inverse, change it to x. So this is just the integral of the fx conjugate. And then I have the pi x inverse, and then I do the dx, okay? But this whole thing, you can think about this as the integral of the I move the fx inside, and then I do the pi x, and this whole thing, I take the conjugate of this operator. And because conjugation is kind of linear, you can move this conjugation to the outside. So let's just pretend it's the conjugation of this entire integral, which is essentially just I pi of f, the entire thing conjugate, okay? So as you can see, the I pi of the involution is the adjoint of the I pi of f. And we have the two little property we need to check. So let me just do these algebraic ones first. So if I do the pi x on the left, and I do pi of I pi of f, so this one is going to be equals to the integral of the fy. I have a pi x outside first, and then let's do pi y dy. The pi is a homomorphism, so you can move everything inside. F is a scalar, so you can commute it to the other side. So this is the integral of the fy, pi of the xy dy, and you use the left translation invariant to cancel out the xy part, make it into a y, so you will end up with x inverse y here, and then you have a pi y dy. This one is essentially just integral of the left translation of f by x pi y dy. So this is I pi of the left translation of f by x, okay? And the right-hand side is really similar, so let me just write it quickly. So if I want to do it right, so you do the same kind of integral. You have f of y, and then you have a pi of y, but now x is on the other side, dy. So when it's on the other side, what you can do is you kind of do the standard trick by first using the modular function, and you integrate f of y inverse pi of the y inverse x, but you need to compensate by a delta of y inverse dy. And then this y inverse x is, you can write it as x inverse y, the whole thing inverse, and then now you use the left translation, okay? So this one becomes the integral of, so all your y will becomes the xy. So in other words, here you will have a y inverse dy, and then here you have an x of the x, y becomes xy, so it really becomes the y inverse x inverse. And finally, the delta is also a y inverse x inverse. All right, and so what you can do is you can pull out a copy of the x delta of x inverse, because that doesn't matter. Okay, delta is a homomorphism to the unit. Well, it's a homomorphism, so you can move that out. And the rest of this, you can write it as the delta of the y inverse, f of y inverse x inverse, and then you have a pi of y inverse dy. And now you do the modular function again, you move the y inverse to y. So this one becomes the delta x inverse, integrate of f of all the y inverse becomes the y, and delta disappear. So I have f of y x inverse pi of y dy. And this one is no other than the right translation by x inverse of y of f evaluate at y. Okay, so this is delta x inverse times the evaluation I pi of the right translation by x inverse of f. Okay, so let's finish this part of these algebraic proofs. All right, and if we want to show it's non-degenerate, let's say for every, let's say u is not equal to 0, so u is some vector inside h pi, I can, by the continuity of this pi, because I know pi evaluated identity is equal to identity, so there exists some, say, v containing E going to be a compact neighborhood, so that for every x inside this V, I have this pi x, because it's close to the identity. So pi x minus u, okay, it's not going to be too close to 0. Okay, so it's strictly less than the length of u. Okay. So if I let f to be this, because v I chose it to be compact, so let's just take high v divided by its left hard measure, let's say mu of v. Then what I can do is that I can consider I pi. So if you consider I pi of f, so this part, so on this v, this pi of x is really kind of bounded away from this u, so this is essentially we want to show that this one is non-zero. So if I consider the difference, okay, so this is going to be equals to the integral of 1 over mu of v, and you do the integral over v of this pi x of u minus u, and then you do the dx, okay. And because on this v, this is bounded strictly less than u, so this one is also strictly less than u. So in other words, this is I pi f of u is not going to be equal to 0. So in other words, I pi f of this u is not equal to 0. So basically it shows every non-zero vector you can basically see is non-zero by some range of the I pi. So I pi is non-degenerate. Okay, so it's non-degenerate. Okay, so this finish the proof.